Okay, so I'm recording this session, guys, now. So again, this is a walkthrough session for worksheet number 1. And we'll start with problem number 1. There are 2 problems in this worksheet. No? So we start with this one. So we will refer to the phase diagram shown below, this one. This is the compressive stress strain diagram taken from Little in 2008. So let's consider the cold rolling at room temperature of a slab with an initial thickness of 20 centimeters. And let's also take into account the effect of elastic strain recovery when we are answering these 4 questions. No? So the first question is, nabasa nyo yung, yung module number 1? Tama? You're familiar with the cold rolling? Malabo po talaga. Ay, hindi kita. Wait lang. Settings. Ay, kaya pala. Naka-standard definition pala ako. Ayan. Hopefully, nag-improve yung quality. Naka 720p na siya. I-refresh ko, no? Para... Hello? Ni-refresh ko yung screen. Ginawa kong 720p. Paano i-full screen? I-click nyo lang yung... Oo. Yes. Tama. Welcome one. Pindutin nyo yung mukha ko, tapos i-pin nyo sa screen nyo para maging full screen siya. Okay? Okay, ayos na. Okay, sorry, by default pala si Google Meet, naka 360p lang, kaya malabo kanina. Anyway, so let's start na. So, again, ang ano natin is, the first problem is involves rolling, which is a type of metal deformation process, no, or a type of deformation processing technique. And it is done at room temperature, and we need to take into account elastic strain recovery. Okay, so if you read the module number 1, you probably have encountered these terms, no? So again, rolling is when we pass a metal or a slab of metal through a pair of rolls, and these rolls will exert compressive forces on our metal slab, thereby reducing its thickness. Okay. So the roll gap, the first question is, we need to approximate the final thickness after passing through a stand with a roll gap of 16. Okay, so if you recall, yung roll gap is the distance between your between the pair of rolls na from which you are trying to pass your metal through, no? So you may argue that if the roll gap is 16, hindi ba yun na din yung final thickness ng slab? So, tama ba? Any comments on that? Mag-random call ako para may interaction tayo konti. So, let's hear from Dainty. Dainty, what do you think?
Sir, naalala ko po sa lesson na kapag mapupul po yung metal, magko-contract.
Ano yun? Sorry, magko-contract? Pag, this is rolling, no? We are pushing your metal.
Liliit siya.
Liliit siya. So,
wala po ba tong height?
sige, you can open up your module 1 class now para just in case you need to refresh your memory on tama ba this is the first time you encountered these concepts at ng mga adaptive metallurgy, or I think slightly na-discuss to sa MetE177, no? Ng konti. Nandito pa ba si Dainty? Nawala ta si Dainty.
Hello po. Hindi po na-discuss sa MetE177.
Hindi na-discuss. Sige, okay lang. Pero anyway, di ba pinapasok natin yung metal natin through the rolls, and the distance between the rolls will give you the roll gap. So the argument is, if yun yung distance between the rolls, then shouldn't it be the final thickness pagka pumasok yung metal doon? Ano yung... Sige, I'll call another one. Thank you, Dainty, sa comments mo kanina. Let's try si Riquel.
Hello, sir. Ang tingin ko, sir, meron pang, may mangyayari pa dun sa elasticity pati sa resilience ng metal. Kaya hindi siya necessarily 16 centimeters din.
Okay, that's very good, Riquel, no? So, that's correct, no? Kasi because of what we call as elastic rebound, the metal will actually retain some of its lost na strain, no? So, if we were to answer this question, we need to take into account elastic rebound, no? So, I think iba yung term na ginamit sa module. Let me just look at the modules, no? I think wait lang. I'm sorry, this is module 2 pala, no? So, the module uses the term elastic strain recovery, no, which is the same thing as elastic rebound, no. It means the same thing. So meaning, whenever we deform our metals and we go past the plastic region, so for example, nagde-deform tayo ng metal, we go past the elastic region, tapos pumasok na tayo doon sa plastic region, nagkakaroon na tayo ng permanent deformation, no. Pero not all of the deformation that was applied to the metal is solely plastic deformation. No? Meron pa ring part doon na elastic in nature, and that elastic part will be retained. So, ibabawiin ni metal kumbaga yun. Okay? So, for this particular case, ang gagawin natin is we will try to identify kung nasaan yung ano, no? So, I'll just mark this ano, no? So, this is a case wherein and take note, class, we are using compressive stress strain diagrams here, no? And this is important because when we do rolling, we are not applying tensile load, no? So compressing your rolling process is what we call as a compressive na deformation processing, no? So there are different types of deformation processing. This will all be discussed later on. Pero yung rolling is a type of compressive load. Although mukhang in some instances pwede kasing yung metal mo ay hinihila papasok doon sa rolls, no? So you can argue na baka tensile in nature yung loads na involved, pero the actual load that is deforming your metal is compressive in nature. This is the reaction of your rolls onto your die. So if you can imagine, I'll just draw it in this side, no? So if you have something like wait lang. I-extend ko lang yung ano ko, no? Okay? So, if you have something like ganito, class, no? So, ito yung rolls mo, kunwari. Tapos, ito yung ano, yung slab natin. Tapos, dito pa lalabas yung metal. Then, you can see that the compressive loads actually involved is this one, no? Ito yung mga compressive load na nagde-deform sa metal natin. So, it's not actually the tensile force that can be applied because in some processes, pwede mong hilain to, pwede ring itulak siya, no? So, it depends on the type of arrangement you have. Pero, the interaction between the metal workpiece, so this is your workpiece, which is usually the slab, no? Usually, pag nagro-roll tayo, you deal with slabs. But sometimes, we can also roll bars, no? Pero in any case, ito yung ano, workpiece natin, ito yung rolls natin. So yung reaction ng rolls and the workpiece will produce the compressive load. So because it's compressive load, and this will be useful lalo na pagka kunwari nagse-search kayo ng ano, no, mga stress strain diagrams that you might want to use for certain problems, you'll have to take note of the type of stress strain diagram kasi there are two types, no? Pwedeng compressive kasi siya, pwede din siyang tensile. So dito binigay naman na compressive, pero for example, kunwari lang sa sa exams or design problems, hindi binigay sa inyo yung compressive yung stress strain diagram, then you'll have to look for the strain diagram yourselves. And if you look for references, you need to take into account, or you need to be very careful kung compressive ba yung tinitingnan nyo or tensile yung tinitingnan nyo. And again, this can be identified by the type of process na ginagamit nyo. So if it's rolling, then obviously it's compressive. Kunwari, if it's forging, it's also compressive. So dapat tingnan nyo yung stress strain, yung type of stress strain diagram niya. Okay? So again, this is a stress strain diagram, and sabi daw it is cold rolled at room temperature, no? So if it's cold rolled at room temperature, then we use this graph, no, itong nasa pinakataas. This is a warm, we can call this as a warm working condition, no? And I don't actually know the exact recrystallization temperature, and this will be discussed further, no? I think nag 146 na kayo, no? Or 176. So you're familiar with the concept of recrystallization. As a rule of thumb, although in 176 we've already discussed na recrystallization is not actually a specific value. It depends on the time and temperature kung saan mo, or it depends on the time kung ano yung binibigay mong time for full recrystallization to occur. Pero in general, because of the sensitivity of recrystallization temperature to time, it appears as if na si recrystallization is a material property rather than a time sensitive na property. So it seems like a material property, and usually ang rule of thumb natin is yung recrystallization is equal to around 0.5 ng melting, no? So if we take the melting temperature of a metal divided by 2, then we get the approximately the recrystallization temperature. So if you're working at higher than recrystallization temperature, then that is, kung mas mataas yung working temperature nyo sa recrystallization temperature, then this becomes your hot working condition, no? Tapos pag lower siya than the recrystallization temperature, then it's a cold working condition. Pero ngayon, merong new term na throw around, no? It's called your warm working condition. So, warm working condition, and this is just additional additional information, no? Warm working condition is when you have, it's greater than room temperature. So, yung warm working is when your temperature is greater than yung room temperature. So it's greater than 25 degrees Celsius. Pero it's less than your recrystallization temperature. So that's what we call as warm working, no? Pero technically, it's still cold working, no? Because you're working at a condition where recrystallization is significantly slower, no? Okay? So, hindi natin kailangan to, no? Pero anyway, we'll use the upper graph kasi ito yung room temperature condition natin. And sinabi naman sa problem na cold work siya at specifically room temperature sinabi, no? So we can use this one. So first step is try to figure out kung nasaan yung yield point niya, no? So you all remember the yield point, no? Tama? From the module 2. Just to check, tawag ako ng random person ulit. Geneva, are you here? Naalala mo kung ano yung yield point?
Yes po. Yung yield point, yung point kung saan mag-permanent na deformation.
Okay, that's correct. Geneva, no? Although the yield point is a very parang finicky siya ng concept class, no? Kasi if you remember, meron tayong different types of points. Meron tayong, wait lang. Meron tayong, kung naalala nyo, yung proportionality limit. Proportionality limit. Meron tayong yield stress. Tapos meron tayong yung offset stress, no? Okay? So, in most cases, when the metal displays something like, kunwari, meron tayong graph na ganito, no? So, this is a typical UTS graph. Tapos, if you look at the typical tensile graph, in most cases like metals like steel, no, etong part na to, there is a stark contrast between your plastic region and the elastic region. So, itong point na to, yun yung sinasabi nating yield point, no? And all of these three, they exist as one point. Sila yung tinatawag na yield point lang. Pero in some cases, like metals like this, no, if you look at this, ang tawag natin dito is it does not display what we call as the yield point phenomenon, no? Kasi if you look at it, itong part na to, hindi siya nag-exist as one point lang. So medyo nagka-curve siya, no? So yung proportionality limit is just in this particular case, proportionality limit, siya yung limit kung saan hindi na nagli-linear yung graph natin. So for example, linear siya, it follows Hooke's law. Pero pagdating dito, hindi na siya linear, then that is your proportionality limit. Okay? Tapos pag in-extend nyo pa siya, kunwari ganyan, so magka-curve na siya. But if, for example, you release the load here, if you release that load, babalik pa rin or marirecover pa rin niya lahat ng strain. So in that sense, hindi pa natin naabot yung yield stress natin. Okay? So the way researchers do this is incremental yung gagawin nila, no? So they start with kunwari na-reach na nila ang proportionality limit, they strain it by a fair amount, tapos release nila, they look at the specimen kung nagbago ba yung dimensions. If not, then therefore hindi pa na-reach yung stress limit. So ulit-ulitin nila yon hanggat umabot sila sa point na kung saan pag nalagpasan na nila yung certain amount of stress, ang nangyayari is meron ka ng irreversible na deformation or yung permanent deformation, no? And that is where nagsa-start na yung, kung ito yung proportionality limit, nagsa-start na yung yield stress. So at this yield stress, ito yung point kung saan hindi na or meron ka ng onset of plastic deformation. Okay? So in general, no, kasi in industry, these are all just interchangeable terms, no? Kasi we are so used to metals that have a yield point phenomenon, no? Or meaning there is a distinct point kung saan nagsa-stop yung linearity tapos nagsa-start yung plastic region. Pero in some metals, hindi kasi nagdi-display sila ng yield point phenomenon, no? So it's also important to know na there are differences between proportionality limit, yield stress, and offset stress. So offset stress is just siya yung tinatawag natin na the limit of usable the limit of usable yield stress. Kasi in industry, there are certain tolerances, no, na allowable sa isang product. So for example, if a product strains by 0.2%, engineers believe, or it is in a general rule of thumb that 0.2% is so small na hindi siya nakaka-affect sa performance ng material natin. So sometimes merong iba yung limit nila, no, pero as a general rule 0.2% yung limit. So kaya siya yung tinatawag na offset stress. So 0.2% is the point wherein kung nagkaroon ka ng 0.2% strain, so if and I'll just blow this image up, no, and or better yet, gawa ko ng isa pang no. Ito, nakikita nyo naman guys, no? So for example, I'll blow this up. So meron tayong graph na ganyan again. So let's just say na nag-experience siya ng yield point phenomenon, no? So the offset stress is if we, for example, nagkaroon na siya ng 0.2% na irreversible na strain. So this is 0.2%. And again, percent to class, no? So 0.2% strain is translated as 0.002. Tama ba? 1, 2. Tama. That's 0.002 strain kapag ginamit natin yung unitless value ng strain, no? Okay, so minsan dito nagkakamali yung students din, no? So this is 0.2% strain. So this is your irrecoverable. Pero again, as engineers, although this is irrecoverable, this is still usable, kumbaga. Kaya tinatawag siyang limit of usable na strain. So if we drew a parallel line dito sa original ano natin, if we drew a parallel line ng ganyan, then kung saan siya tatama dito sa plastic region natin, ito yung tinatawag na offset stress natin. So I think this is discussed fairly in great detail doon sa module, no? Pero I'm just emphasizing it, no, just in case na hindi siya malinaw doon sa module natin. Okay? So far nagigets pa naman yung sinasabi ko, class, no? Pwede bang wala kasing thumbs up pala dito. Pwede bang kahit okay kayo? Yes, sir. Okay, thank you, Dainty. Yes, thank you guys sa confirmation. Okay? So, again, ito yung offset stress. So, in most cases, in most cases, gusto natin gamitin yung offset stress, no? Kasi siya yung, kumbaga, medyo may tolerance siya. So, hindi siya strict doon sa ano niya. And the tolerance is enough na in engineering terms, usable pa rin yung material natin. Okay? So balik tayo sa original problem natin, no? Again, dito, wala tayong yield point phenomenon, no? So, ang gagawin natin is, we try to estimate kung nasaan yung tingin natin, nag-stop yung linearity niya. So, I'm thinking somewhere here, no? So, you could have different values, pero this is what I think is, or kaya ang problem just states na we are to estimate, no? Kasi hindi natin fully makikita talaga to. Pero anyway, we take this value. Tapos, ang gagawin natin is, we use the offset stress, no? Okay, so whenever your material does not display a yield point phenomenon, it is always practical to use an offset stress. So we'll use an offset stress, no? So if this is 0.1%, then somewhere here is 0.05. So 0.05. So dito ay, wait lang kung ito ay 0.5, so that's 5%. 1% is somewhere dito. So 0.2% is sobrang liit, no? I'll just say somewhere dyan. Okay? So siguro this becomes a bit of estimation work na. So if I do a parallel line, and I'll just siguro gaganon ko para medyo makuha ko yung parallel, no? Oop. Hindi kasi siya linear pala. Let's just say, yan, linear yan. I do something like that. Then this is my 0.02 offset stress. So maybe I'm off by a bit, no? Pero you can make it as accurate as possible. Pero dito yung nakikita kong offset stress. So this is now the stress na tinitingnan natin. Okay? Okay. So from here, dito na tayo mag-start sa ano natin, no? Sa parang sa ano tawag dito? Kung saan natin siya by the way, iba pala yung problem mo. Hindi pa pala, sorry guys. Hindi pa pala hinihingi yung offset stress ito, no? So I'll just cancel this out, no? Ganyan ko lang. So the first problem pala muna is trying to determine kung ano yung magiging final thickness niya. Okay? So, gagawin natin is we take note that it is being compressed. It is a thickness of 20. Tapos, kinocompress natin siya to 16%. To 16 cm. So, that's yung amount of strain natin is equal to 20 minus 16 over 20. Tama? Kasi it's just the change in dimensions divided by the original length, no? So this is engineering strain, of course. So this is 4 over 20, which is, tama ba? 0.2, no? 20%? I think it's 20%. So it's 20%. So dito siya, 20%. If we project it upwards, then we'll see na dito yung strain, dito yung magiging point natin dun sa curve. Okay? So this is the final point sa curve natin when it experience the 16% na or when it experience the compression that compressed it to the roll gap of 16 cm. Tama? So if we take the linear na so if I'll do the parallel ulit, no? So something like ganyan siguro. Mali pala yung initial na ko, no? Mukhang hanggang dito lang ang parallel. Tama? So if I do that, then from here, I can draw a parallel line. And I can determine kung alin dyan ang irrecoverable tsaka yung recoverable na strain. So I'll just mark this, no? So let's just say ito yung X. Tapos ito yung Y. Okay. So I'll call somebody again. So tingin mo, let's go with Ivana. Tingin mo, Ivana, alin dyan yung recoverable strain at alin dyan yung permanent na deformation? Is it X or is it Y?
Wait lang po.
Sige, pag-isipan mo.
Kasi nanay ko tinatawag po ako.
Ay, sige. So, I'll just call another person na lang muna, Ivana, ha? So,
may klase ako!
sige.
Sige po, wait lang po.
Sige lang. Sige, medyo busy si Ivana, no? So, let's call on John Alfred. John? Nandyan ka ba?
Sir, yung Y po, sir.
Yung Y, that's correct, no? So, meaning, kung ito yung recoverable strain, si Y, so this is the strain na i-bounce back niya. Tama? So, the final dimensions, how should we compute the final dimensions pag ganito? So, hindi na magiging 16 yung final, no? Kasi meron pang part na ni-recover siya. Tama?
Yes po.
Okay. So, this is, I can estimate this as 0.15 siguro, no? Tama? We have the same estimate. So, ibig sabihin, 0.15 na strain lang yung permanent deformation ng metal natin. Okay? So, I think you can, from here, you can figure out kung ano yung magiging final deformation, no? So, you can use this 0.15 na strain para i-compute yung final na deformation. Okay? So, I won't be giving the final answer, pero I'll just be giving some a few initial na calculations para lang to get you started with the calculations, no? So, hopefully, this helps. From this 0.15, there are actually two ways to solve it. Pwedeng bawasan nyo yung recoverable or i-compute nyo using yung permanent. So either way will give you the same answer, no? Okay? Or I mean, either idagdag nyo to sa final dimension niya or you use this value para makuha yung final dimension. Okay? Okay, so that's for number 1. Let's go to number 2. What is the expected yield strength of the rolled metal in 1? So I think you can solve this on your own, pero just to help you out, guys, no? Let me just give you a sort of review on what happens when we plastically deform a metal, no? So when we have, and let's draw another ideal na tensor stress strain diagram. So this is our ideal stress strain diagram na meron siyang yield point phenomenon, no? So when we when we try to deform our metal, so for example, ganyan, no? Then we applied load sa metal natin, then it will follow this curve, no? If it's the same material, then it will follow this curve. Then past this point, magkakaroon ka na ng plastic deformation, tama? So you get a plastic deformation hanggang dyan. And let's just say, from this point, tinigil mo yung loading, no? And ni-release mo yung loading ng metal natin. So what happens is, it will recover some of those stress. Tama, no? It will do something like this. It will recover it. Tapos, as we mentioned earlier, ito yung recovered elastic strain or elastic rebound. Tapos ito yung permanent deformation niya. Tama? We've already noted na ganyan yung mangyayari, no? Mga class, no? So, if we try to do the experiment again, kunwari, say etong metal na to, na-deform na siya, tapos gusto natin siyang i-expose ulit sa stress strain diagram, then we will have something like this, no? It will still follow Hooke's law sa elastic region because yung elastic behavior niya is still the same, no? And let me just use a different color para mas malinaw siya, no? So, it starts here. It still follows Hooke's law kasi it's still the same metal following the same elastic properties. Pero, pagdating dito, hindi na siya mag-yield at this point, no? Because your metal has been compressed and it has undergone plastic deformation. Therefore, nagkaroon na siya ng strain hardening. Okay? So, because it underwent strain hardening, mas mataas actually yung magiging yield strength niya. And in fact, when you continue this, the point wherein magko-continue siya to deform, plastically deform, will be the same point kung saan siya tumigil last time. Okay? So for example, tumigil kayo dito, then if we project it towards this line, ito yung starting point kung saan titigil yung, or magsisimula yung plastic deformation. Parang ganyan. And let's just say we did the experiment again, tumigil tayo dito. And we did another experiment, in-unload ulit natin siya. Then, ang mangyayari is, if we try to load it again, itong purple line na to, gaganon siya, ito na yung new yield point niya. So, it will start here, tapos magkakaroon ka na ng plastic deformation again. Parang ganyan. So, this value, yung change, instantaneous value na to, it's a changing value, no? Tama? Kasi parang every time we stop and start our deformation, we change actually the yield point, and we call this yield point as, and we will use this a lot, no, sa adaptive metallurgy. We call this as the flow stress. Okay? So flow stress simply is just the yield stress needed to continually to continuously plastically deform our metal. Okay, malinaw ba 'yon? So for example, if you stop here, then the amount of stress needed para mag-cause ka ulit ng further deformation is this point here. This will become your flow stress. Sometimes sigma F yung tawag nila sa flow stress, no? Other times there is also sigma prime. You can also use sigma prime. So this is an important concept, class, no? Kasi in most cases when we are computing for your plastic, when you're computing for metal working loads, hindi yield point yung ginagamit natin, no? We use the flow stress value. Okay? So, malinaw ba yung concept of the flow stress, class? Meron bang questions about it? Can I get a okay or thumbs up sa chat? Para lang alam ko na okay. Some have confirmed na malinaw. Riquel, thank you. Meron bang muddy points na gusto kayong i-clarify? Okay, so I think you get the concept of flow stress, no? So again, flow stress is important because ito yung value na ginagamit natin when we are computing for metal working loads. So with this flow stress, I think you should be able to answer this question, no? So it is related to the flow stress, no? Okay. So next is number 3. What is the maximum allowable roll gap for a fresh workpiece? Maximum allowable roll gap. Ay, di-discuss na ba to? Okay. So to answer this question, we need to review the parts of a stress strain diagram, no? So if we look at something like ganito, and I'll just erase this again. So kunwari meron tayong stress strain diagram na ganyan. Tingin nyo, ano yung portion? So just to review, no, marami tayong parts dito. So this is our yield point if it experiences a yield point phenomenon, which can be broken down into proportionality limit, yield stress, and offset yield stress. No? Tapos meron tayong yung highest point, which is our UTS. Tama? Tapos we have this point here, which is our fracture point, which can be expressed either in terms of strain. So yung strain at which fracture occurs, or pwede rin express siya as stress wherein the fracture happened. No? Okay? So then we have the modulus of elasticity, which is our Hooke's law. Tapos we have two areas under the curve. No? So pag area under this, under the elastic region curve, ang tawag natin doon ay resilience. Tama? Tapos pag area, resilience nga ba? Wait lang, let me just. Tama, resilience. Yes, thank you, Juan. So, if area under the entire curve, ang tawag natin doon is toughness, no? Tama? And the way I think about it is, kaya maganda tong metals, no? Kasi para siyang, yung terms na ginagamit sa kanya is analogous to parang mga terms na ginagamit natin for people, no? So for example, if we say a person is resilient, so meaning kahit anong stress na ilagay natin sa kanya, he does not kumbaga hindi nagbabago yung tao na yon, parang ganoon. I hope that makes sense, no? So when a person is resilient, pag kahit anong stress na ilagay mo sa kanya, he will still bounce back, babalik pa rin siya sa parang ano niya, or hindi magbabago yung pagkatao niya, kumbaga. So kaya resilient siya because it's the area under this curve, no? So kahit anong stress ang ilagay mo, he will always come back to yung original state niya. So that's resiliency. Tapos toughness naman, toughness is unique, no? Because yung toughness is the amount of, we can roughly define it as the amount of energy that a material can absorb without it breaking. So in terms of people, para siyang gano'n, no? Toughness is something like that. So it's the amount of stress, amount of strain na kaya mong tanggapin without you actually breaking, no? Parang gano'n, na parang hindi ka magbe-breakdown. Although nag-yield ka kasi at some point parang you experience enough stress na you actually change a part of you, no? So sometimes it's for the better. So, and in most cases, or in metals, it's for the better, no? Kasi when you plastically yield, you become stronger. And pwede din in terms of people, when you plastically yield, then you become stronger as a person, no? Tapos when we talk about toughness, it's parang the amount of stress na kaya nating tanggapin as human beings, tapos without us breaking down, no? Na hindi tayo magbe-breakdown. In fact, we become stronger from it, no? Tapos yung breaking point natin will be in terms of metal, siya yung fracture point. So it's the point wherein when we reach a certain amount of stress, hindi na natin kaya, no? So that becomes our breaking point. So although this could mean na we become broken metals, no? Or if we are people, we become broken. And I say this as a joke, no? Pero it could be true. It only takes a metallurgist para maging whole again ka. So pwede kang i-remelt para maging new metal ka or new person ka. Pwede ring i-weld ka para ma-fix yung broken pieces mo, etc. Parang gano'n. So it's a sort of corny na analogy, no? Pero ito yung parati kong ginagamit kasi I'll just start recording again. Okay. Ito. So yun, kaya gusto ko yun kasi it uses terms na parang ano, no? We experience every day in real life as human beings, kaya mas madali kong natatandaan kung anong ibig sabihin ng when applied to metals, no? So it could help you para maalala tong mga terms na to, no? Pero ayun, so just try to think about it, no? So pwedeng ganun. Okay? So we've discussed different points dito sa graph natin. So tingin nyo, ano yung pwede natin gamiting graph doon para i-answer tong problem na to? Okay? So what does it mean when we say na ano yung maximum allowable roll gap? So I'll call, sino bang hindi ko natawag? Si John, si Rebo. Si Rebo. Rebo, tingin mo, ano yung value dito na pwede natin gamitin for part 3?
Kasi siguro po yung dun sa fracture point.
Fracture point?
Dito.
Ano yung parang basis mo doon, Rebo?
Kasi pag mas mababa pa dun yung roll gap, magpa-fracture na po yung metal, so hindi na siya useful.
That's okay. Thank you, Rebo. That's correct, no? So, we can't go past the fracture point, no? Kasi if we applied stress past the fracture point or we applied strain that is past the fracture point, then yung metal natin, paglabas niya, na nagkakaroon na siya ng imperfections or impurity or nagkakaroon siya ng defects, no? And this occurs in most metal deformation process, no? Kaya kinocompute tong mga values na to kasi um, sometimes gusto kasi natin na as engineers gusto natin i-improve yung process, no? So increase yung efficiency na isang process. So the way we increase the efficiency of a process is to get the maximum amount of deformation per roll, no, or per stand. So if it's, for example, sa rolling, it's per stand, kailangan per stand, maximum yung amount of deformation mo. Kung when you have something like drawing, then it's per stand din. So per die na dadaanan mo, kailangan naka-maximum siya. Pero hindi ka pwedeng lumagpas sa maximum because you will experience defects and kumbaga hindi mo mako-continually deform yung material mo kasi meron na siyang defect sa loob, which becomes your what's the term? I forgot the term. It becomes your stress concentrators, no? So lalo na kahit small breaks lang siya, it becomes stress concentrators, eventually leading to catastrophic na failures, no? So in specifically in drawing, ang tawag dito is the maximum drawability, no? So there is a maximum value for which you can draw a certain material, a certain percentage of that material. In general terms, nawala ang audio. Wait.
Sir, hindi naman.
Baka na ano mo, na mute mo ako, Rebo. Baka na mute ako ni Rebo. Meron na po ulit. Okay, sige. Thank you. So yun, parang ano yung sinasabi ko? Yung in general terms, ang tawag sa kanya is yung cold working, no? So this is the maximum cold working na kaya nating i-apply sa isang material. In general, kaya natin i-increase yung maximum value by using hot working conditions, no? Hot working conditions in general can achieve larger amounts of deformation because ina-apply natin yung recovery in conjunction dun sa strain hardening, no? So kumbaga the recovery rate is almost equal to the strain hardening rate, therefore hindi siya nagkakaroon ng defects. Okay? So with that, hopefully kaya nyo nang masagot tong maximum allowable roll gap for a fresh workpiece pagka in-apply nyo yung Sigma F. Yes. Yes.
Sir, question po. Yung elastic rebound po ba, applicable hanggang sa fracture point?
Yung pagka engineering stress strain diagram siya, no? Hindi siya masyadong applicable because when I talk about the familiar kayo sa engineering stress strain diagram versus the true stress strain diagram? Familiar ba? So pagka meron tayong stress strain diagram na ganyan, this is an engineering stress strain diagram. Pag kinonvert natin to true stress strain diagram, it becomes something like this. Okay? So in most cases, nagme-make sense tong true stress strain diagram because if you think about it, kunwari itong engineering stress strain diagram, sometimes it doesn't make sense, no? Kasi kunwari past this point, this is your UTS, tama? So past the UTS, parang nakikita natin na it actually takes a smaller amount of stress para mag-induce ka ng larger amount of strain. Tama? So for example, dito sa point na to, this is a smaller stress than the UTS kasi si UTS kasi yung maximum mo kung saan siya nag-plateau. And it doesn't make sense na kung bakit sa point na to, konti yung stress na kailangan mo para mag-induce ng this amount of strain, no? And you can observe this in everyday na objects, no? So for example, if you want to deform some material, you always need larger and larger amount of stress para maka-induce ng more and more strain, tama? That is the intuitive na parang understanding natin of how materials behave, no? So the fundamental na siguro flaw dito sa engineering stress strain diagram is the formula for engineering stress strain diagram, let's just S siya. S is equal to F over A naught, where A naught is the initial na area. Pero take note that when we are deforming your metal, so for example from this area, when we deform metals, it becomes thinner and thinner, no? So A does not actually A is not actually a constant, tama? So kung tutusin, engineering stress strain diagram is actually just a force. It's not actually a stress strain diagram, no? Technically, hindi siya stress strain diagram. Para siyang force change in L diagram or change in dimension diagram. So kaya hindi ganun ka-accurate yung behavior ng engineering stress strain diagram. But if you convert this to true stress strain diagram where your S now, and usually pagka true, we use the Greek letters, so we have sigma. So I'm not sure na to. Has this been discussed sa 146 nyo o 176? True versus engineering? Okay, yes, na-discuss na pala. Okay, that's good, no? So just a recap, pagka pagka true stress that's given as sigma equal siya sa instantaneous strain. So this because it's instantaneous strain, lumiliit yung value ng area natin and therefore tumataas yung stress value as it proceeds with this with this curve, no? So kaya dito it makes a lot more sense through stress strain diagram kasi at any point you will actually need higher amount of stress para maka-achieve ka ng higher amount of strain, no? So in this case, pwede niyo gamitin yung yung elastic na rebound na yung parallel line. Pero in general, past the UTS kasi kaya siya problematic because let me just draw, no? When we do the tensile stress or the compressive stresses, the point where so magkakaroon tayo ng ganito, something like this. So if we increase the amount of stress, mag-thin out yung metal natin. So ito yung dog bone natin, mag-thin out siya pero mag-expand siya ng ganyan. Expand siya. Tapos aabot siya sa point kung saan nagkakaroon ka ng necking, no? So necking is this is related to the point where we have your UTS. So when we have necking, nagkakaroon ka kasi ng micro voids dito sa portion na to. And this micro voids causes your material to behave differently, no? Or mas nagiging susceptible siya or mas sensitive na siya to stress, no? So it actually takes smaller stress na para to continually or the stress values have continually increased with lower amount of forces. Okay? So kaya and I'm going all around the place now, pero kaya si stress strain diagram is going lower kasi yung force mo, again, technically this is just a force change in L diagram, no? So the force is lower dito sa portions na to kasi the area is smaller, no, is getting smaller, and it actually takes lower amount of force to produce higher amount of stresses. Kasi if you notice, dito sa portions na to, when you have microvoids, nagkakaroon ka ng stress concentration, no? So the voids become stress concentrators. Therefore, it amplifies the amount of stress na available sa inyo with a lower amount of force value that is applied, no? So, in that sense, anything past the UTS is not anymore an accurate representation ng behavior ng material natin, no? Without defects. Kasi past dito, nagkakaroon ka na kasi ng defects. So, medyo, in a way, hindi na accurate yung behavior niya. So, to answer your question plainly siguro, ang dami kong sinabi, pero to answer your question plainly, anything past the UTS, so if this is UTS, anything past the UTS, hindi mo na magagamit yung hindi mo na magagamit yung technique na kung baga ka parallel para makuha yung recoverable strain. Anything dito uncertain na yung behavior niya. And in fact sa true stress strain diagram, no? When we do true stress strain diagram, and I'll just do this again. If you have something like ganyan, ito yung UTS. Sa stress, if you convert this to a true stress strain diagram, you actually have hanggang UTS lang siya. Tapos past the UTS, ito is a modeled behavior na lang to. Hanggang sa fracture point. So modeled in a sense na kung ano yung slope dito, kukunin niya tapos i-project niya outwards. Parang ganyan. Okay, so I hope I answered your question adequately. If you if you have more questions, i-send nyo lang sa ano, no? Okay, sir, allowable pa rin po ba? Sorry. Wait lang. Nawawala kasi yung chat sa akin. Chat. Sir, allowable pa rin po yung kahit mag-necking na yung metal. I'm not quite sure what you mean here, Rebo, no? Can you,
Ay, sir. Doon po kasi sa, yung sa question kayo na sa number 2, yung allowable roll gap. So, pwede pa rin po ba yun kahit lumagpas na ng UTS, allowable pa rin po ba yun?
Pwede pa rin. So, the thing about compressive loads, no, is hindi kasi siya as susceptible to failure as compared to tensile loads. Kasi when we have a tensile loads, nagkakaroon tayo ng microvoids, tapos yung microvoids natin na elongate natin siya, ganyan, and eventually mag-increase siya. Pero in compression, if you have microvoids, when you start experiencing microvoids, yung microvoids na yun does not have the same negative impact as compared to tensile loading. So kaya okay lang gamitin natin yung doon sa allowable na roll gap question, pwede natin gamitin past sa UTS. Okay, so in general kasi you might have heard this from previous classes, pero in general, metals are always stronger in compression than they are in tension, no?
Okay, thank you po, sir.
Okay. Okay. So, okay na tayo dyan. So, let's proceed with what is the final product thickness at the roll gap in number 3? Okay. I think this is related doon sa kung kaya tinatanong ni tama ba? John Alfred? Kung bakit mo tinanong yung hanggang kailan lang pwedeng So, yun. This is a sort of difficult question to answer, no? So, you can have actually 2 answers dito. Pwedeng you can stop at EF or pwede rin sa EUTS, no, ang gagamitin nyo. So, yeah, I think you can do either, no? Either of these conditions. Tapos you'll have 2 answers that are different pero both answers will make some sense, no? Or acceptable pa rin yung both answers. So yun
Pwede po pa ulit. Ano yung 2 possible?
Pwedeng ang gamitin mo na sigma or na epsilon is yung epsilon at UTS, or pwedeng gamitin mo is epsilon at F. Although dito kasi sa, and this is ano no, a good manifestation of bakit in compression metals are always stronger in compression, no? You can see it in the graph, no, na wala actually plateau dito. You don't experience plateau. Tama? So tumigi lang siya bigla dito. So this is, I'm assuming ito yung fracture point niya, no? So wala siyang UTS kasi specifically because hindi niya na-experience yung necking behavior, no? Or hindi negative yung impact ng necking behavior. So okay, I'll retract my statement to. Pwedeng sigma F lang gamitin nyo. Itong point na to, sigma F. Tapos if you observe, pwedeng gamitin yung 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 sa buong curve na to, pwede nyo actually gamitin yung parallel line technique para makuha yung yung ganitong technique para makuha yung recoverable strain.
Okay, sir. Thank you po.
Okay. Thank you for those questions, no? Mas na clarify natin yung problem natin. Okay? So, we have 30 more minutes. Pwede natin tingnan din yung problem number 2. So for some metal alloys, a plastic true strain of 0.025 is produced when a true stress of 360 megapascals is applied. For the same material with an initial length of 500 millimeters, how much will the elongation be if a true stress of 405 MPa is applied? Assume a strain hardening exponent value of 0.2%. 0.2. Dito 0.2%. 0.2. Okay, so I'll ask a few questions, no? So tingin nyo, ano yung relevant formula dito sa question na to? There's actually only one relevant formula, no? That we will use. I'm thinking about it. Posible ba yung graphical approach? I think posible din, no? Sino yung iniisip nila is gagamitin yung logarithmic approach kung saan titingnan mo yung slope niya in terms of a logarithmic function. May ganun ba yung initial na iniisip? Kasi it can actually also work, no? Pero I think most of you will be partial to employing the power law. Tama? Oh, nawawala nga si Nicole, no? Kanina pa siya pawala-wala. Okay. Na-record ko naman yung session, so pwede kong i-upload to para pwedeng i-view na lang ni Nicole after. Okay? So meron bang nakaisip na gamitin yung power law? Wala? Ano yung si Juan, naisip mo Juan gamitin si power law? Meron bang iba? Ano yung initial na reaction ng ibang students? Sige, tawag ulit ako. Riquel, meron kang naisip na strategy dito?
Sir, nung tinignan ko yung module, nakita ko, pwede siyang i-apply sa whole naman. Parang dalawang equations yung gagawin para makuha yung constant na K. Pero hindi ako sure, sir.
Actually, tama yun, tama. So actually, you'll use the power law, no? Tama. Tapos, hanapin mo yung material constant K. Tapos, pag nahanap mo na yun, pwede nang i-apply, no? So, that's, tama yung strategy ni Riquel, no? I think that's one solution. And actually, yung isang solution is a sort of graphical approach, no? But we can use the general equation of the power law, which is K multiplied by sigma raised to N. This is our power law, no? And we can use this since given yung may initial tayo na values, no? Given tong sigma, tama? Tapos, sigma value, tapos given din yung strain value, and given din yung exponent value. Therefore, we can solve for K. And when we have K, then we can now solve for yung true stress yung elongation niya if a true stress of 405 is applied. So, kung meron na tayong K, ang unknown naman natin is ito yung magiging unknown, si epsilon, no? So, if we solve for epsilon, we get the strain value, then from the strain value, we can compute for elongation. But take note, class, no, na ito is mga true stress and strain values to. So, you have to do the parang conversions if you want to employ engineering na stress strain values, no? Okay? So, by the way, thank you, Rikiel, no, sa answer mo. Okay, um, I think yun lang for the walkthrough, no? Hopefully, you've learned something or natulungan ko kayo in some way sa pagsagot ng Module 1. And we'll still have around 20 minutes, no, left in our session. So, pwede natin i-dedicate to consultation. Meron bang medyo may mga muddy points ba doon sa module natin na gusto nyo i-clarify? Kahit i-chat nyo kung nahihiya kayong magsalita. I think wala masyado, no? So anyway, pwede sigurong wait lang. I'll share ko lang tong yung natin, classroom natin. So I've already uploaded yung stress rate, no? So meron na din siyang module for it. Tas I think you can start with module 3 and I'll upload module 4 na rin, no, sometime soon kasi baka maaga kayo matapos sa module 3. After module 3, magkakaroon tayo ng worksheet number 2. Tapos yung worksheet number 2, I think sa next week natin to siya i-discuss, no? Itong stress rate. So again, we'll have a similar na setup kung saan magdi-discuss ako ng ng kung paano i-calculate or parang lang general starting calculations para to lead you in the right direction, no? Okay, pero try to do it on your own muna. Tapos during the session, try to parang give your feedback kung ano yung initial nyo na strategy on how it differs from the strategy I presented kasi posible din na tama din yung strategy nyo, ibang way lang siya of solving it. Okay? So, ano pa ba? Mayroon pa akong i-discuss dito sa wait lang. Ano nga yung changes? Okay. Ito pala. So, naglagay ako ng consultation board dito kasi baka may iba sa inyo na nahihiya magtanong, no? So, meron consultation board dito. If you ever have questions about certain topics or anything related to MetE177, punta lang kayo dito sa Padlet na to, no? So, this is a Padlet consultation board. Lagay lang kayo ng questions nyo. You don't have to log in, no? So, pwede kayong magdagdag lang ng question anonymously. Tapos, sasagutin ako or sasagutin din ni Juan yung questions nyo regarding the course, no? Okay, so hopefully we can use this, no? Kahit tingin nyo it's a simple problem na baka nahihiya kayo kasi iniisip nyo na iisipin namin na ano ba yan, sobrang simple, nagtatanong ba? No, every question here is accepted, no? Lalo na ngayon kasi tayo, naka remote sessions, no? So yung pag-deliver ng modules is very limited, no? Yung understanding na makukuha nyo from modules alone is very limited. So we always need to have constant communication dito para ma-achieve natin yung mga objectives natin for the semester. Merong chat. Wait lang. Ano yung chinat? Sir, when po due yung worksheet 2? Worksheet 2 is due on, hindi ko pa pala na nalagay, pero it's due on, we can see it here. It's worksheet 2. It's due on September 28. Bakit same siya? Wait, something's wrong. Kasi due ang Ano ba to? Review of... kasi 1 week lang dapat yung ano, no? So, dapat pala... medyo mali yung ano ko. Hindi ko sa... Sige, kaya pa naman natin habulin, no? 23. Dapat pala tapos na kayo. Oh, it's expected na tapos na kayo sa ano, no? Dapat pala tapos na kayo sa stress state. May nakapagbasa na ba ng stress state? Kaka-upload ko lang ba nito? Hindi ko kasi maalala eh. Kasi merong ano, no? Okay, kaya pa naman natin habulin to, no? So, I think I'll just, para maano, no, mahabol natin to, okay lang ba magkaroon tayo ng consultation session on Tuesday? So, I said every Thursday lang tayo, pero on the 29th, ano tayo, work through or magkaroon tayo ng walkthrough sa worksheet number 2. Tama? Tapos pwede sigurong i-due natin, the worksheet 1 is June 28. Pwedeng on the October 1st ang due date ng module worksheet number 2. Okay? Okay lang ba 'yon? 29 mag-meet tayo. Okay. Thank you, Rigel. Thank you, Rebo. Thank you sa mga comment. Ivana, thank you. Ikaw, Juan, available ka on Tuesday?
Yes, sir.
Okay, so let's meet on Tuesday. Tapos, I think most of you have classes on before 11:30, no? So, sige, 11:30 ulit tayo. Okay? So, may mga questions pa ba? Kaya naman to. Stress state is a doable na topic. Tapos, yield criteria, ito yung actually na-discuss na to ng konti sa ES10, ano ba yun sa inyo? ES13 kasi sa amin eh. 102 nyo ata to? Yung mechanics of deformable bodies. Statistics pala. Statics. ES101, tama ba? Na-discuss na to sa inyo? Yung yield criteria. Have you heard of the term Tresca criteria and von Mises criteria? Kung saan diniscuss yung Moore circle. Meron bang nakakaalala sa Moore circle? Ikaw, Juan, naalala mo malamang ang Moore circle. Tama ba, Juan? ES13 ka pa rin? ES13 yung sa'yo, no? Yung curriculum mo. Okay, yes. Sa'yo. So,
102 ata. Yeah.
Okay. Yung Moore circle po after pandemic. Ito yung mahirap pala.
Oh, yeah.
Kasi na-cut off yung ano nyo during the pandemic. Okay, so, sige. For the next week siguro, 2 yung session natin, no? Para mas matutukan natin siya. So, 21 and 1 will meet. Tapos, posible 6 and 8 will also meet, no? Okay lang ba yun?
Okay.
29 and 1, 6 and 8. Tapos, yung sa iba na hindi makakapasok sa synchronous session, again, i-re-record ko na lang yung session para at least pa rin yung balikan, no? Okay, so, yun lang siguro muna for today if wala kayong other questions. So, thank you for taking the time to come today, guys, no? So, salamat din, Juan, para sa ngayon, sa pagsama mo sa meeting.
Yes, sir.
Tapos, kung may concern kayo, kasi baka nahihiya kayo sa akin, itinatanong nyo naman kay Juan, no? Tama ba, Juan? Na active naman sila sa pagtatanong sa'yo?
Wala pang nagtatanong.
Wala pa ba? Sa MetE177 pala yun, no? Yung medyo active.
Yeah.
Okay. So, guys, huwag kayong mahiya magtanong, no? Kasi MetE177 is medyo calculation heavy kasi siya. So, medyo mahirap talaga siya kung hindi kayo lalo na kasi remote learning tayo ngayon, no? Okay? So, are there no more questions? Meron pa ba? Can I get sa chat box? Kahit sa chat box lang kayo mag-confirmation. Wala na po. Okay, thank you, Rigel. Thank you, Dainty. Jan, thank you. Okay, thank you, everyone. Okay, so if ever may tanong kayo, just use our Padlet, no, para magamit naman natin siya. Tapos, or kung hindi kayo comfortable sa Padlet, pwedeng email nyo ako or pwede i-chat nyo si Juan, any of us. We will respond to you as fast as we can. No? Okay, so thank you everyone. I-end ko na rin yung recording natin.